This video is about integrals of trig functions, so a little bit more practice, specifically with integrating trig functions. Considering the derivative of sine x is cos x, that we know, and the derivative of cos x is minus sine x, it's logical to assume that the integral of sine x dx is equal to minus cos x plus c. The integral of cos x dx is equal to sine x plus c. Similarly, if you have the composition of a sine or cosine function with a linear term, you get the following expressions, okay, which are the same as when we learned about integration with a linear term before. This 1 over a is the important part that accounts for the chain rule. Furthermore, if needed, you can use the substitution method to find integrals that are in the form f at g at x times g prime at x dx. An example of this with a trig function would be the integral of 3x squared times sine x cubed, and we'll look at some examples of this in the video. The first two examples that we're going to do is basic trig integration and then trig integration with a linear term. Here, for example A, we can separate our integral into two pieces. 3 times the integral of sine x dx plus 2 times the integral of cos x dx. Okay. Here we can integrate sine x to be minus cos x plus c1, and then we can integrate cos x to be sine x plus c2. When we combine all that together, pulling my sine term into the front, I get 2 sine x minus 3 cos x plus c. You can double check if you take the derivative, you end up with your integrand. Okay, let's take a look at example B. Here we've got trig integration with a linear term. Now we just have to account for this 2. That if we were to take the derivative of our final answer, we would end up with a 2 multiplied by our function. So we're going to account for that by putting a half, or 1 over a. Integral of cos is sine. The linear term stays the same. I'm doing indefinite integration, so I need to add a c. Let's move on to the next two. These are examples of integration using substitution. So this first one, my term outside, or my function outside, is the derivative of my function inside. So let's let u equal e to the x. Then if I take the derivative, the function happens to stay the same. And then I'm going to rearrange for dx to make sure that I've done my substitution correctly. Now I'm going to make my replacements. So I'm going to leave this e to the x outside the same. I'm going to replace the e to the x on the inside with u. And then I'm going to replace dx with this expression that I created over here, circled in red. So now I've got du over an extra e to the x. I'm going to cross those out. Now I've got the integral of cos u du, and that's easy because I know that the integral of cosine is sine, plus c. And then I'm going to resubstitute my original function, and that gives me my final answer. Let's do one more using substitution. Now I've got a polynomial term. So let's replace okay. So let's replace, let's let 3x, let's do this, okay? So let's let u equal 3x to the 4, and we'll see what happens. So here we've got du by dx. Here we've got 12x cubed. So this is good, this x cubed part, because that matches what I have out here in front. And then I'm going to do the same thing. So I'm going to rearrange for dx. So now I've got du over 12x cubed. So let's make my substitutions. So I've got the integral of x cubed. I'm going to leave that alone. Then I'm going to have cos u, because I made that whole replacement. And then again, so I'm circling in red my expression for dx. I'm replacing dx with du over 12x cubed. Now the only part that I'm canceling out is the x cubed. My 1/12 is still there, and I can pull that out in front. So now again, I've got the integral of cos u. Integral of cos u is going to be sine u plus c. And then I can replace, I've got 1/12 sine 3x plus 4 plus c. Same thing here, you can check. If I were to differentiate this answer right here, I would get exactly back to what I started with in my integrand. Excellent. Okay, the other part of this video is that we can actually use the fundamental theorem of calculus to calculate definite integrals. Those first 4 examples that we did were all indefinite. Here we're just going to do 2 examples with definite integrals that involve trig functions. So let's look at the first one, 0 to pi over 6 of 2 cos x dx. Also stretches your brain a little bit, gets you practicing some of those special triangles. So I'm going to pull my constant out in front. I've got 2 cos x dx evaluated from 0 to pi over 6. I can integrate that to get sine x, and I'm going to evaluate at pi over 6 and 0. My 2 is out in front, and I've got sine pi over 6 minus sine of 0. Sine 0 is just 0. What is sine pi over 6? Good question. Let's draw our special triangle that has pi over 6, pi over 3, and 90. Okay, and our matching sides. Now I know that sine of pi over 6 is going to be my opposite side over my hypotenuse, 1 over 2. So I've got 2 times 1 over 2, which is just 1. Okay, one more example. Here we've got 2 sine x plus sine 2x integrated from pi over 4 to pi over 2. So let's separate this a little bit. We've got 2 pi over 4, pi over 2, sine x dx plus the integral from pi over 4, pi over 2, sine 2x dx. You don't really have to separate them into its parts. You could do it all in one step if you wanted to. I find this just helps me get all the substitution and signs correct. So the integral of sine x is minus cos x, and I'm evaluating at pi over 2 and pi over 4. The integral of sine 2x, again, is going to be minus, and I just have that 1/2. So I've got minus 1/2 cos 2x, pi over 2, pi over 4. So now I'm going to substitute in my limits. So I've got minus cos pi over 2 minus cos pi over 4. Make sure you're getting all your signs correct here. Plus minus 1/2 cos. See, 2 pi over 2 would just be pi. And then I would have minus 1/2 cos pi over 2 here to evaluate this one. So I'm going to simplify a little bit, get rid of some signs here, and evaluate. So let's see, I've got cos pi over 2. That one's going to go to 0. That makes my life easier right off the bat. So then all I'm worried about is minus minus plus cos of pi over 4, which is 1 over root 2, plus, let's see, I've got cos pi. What's that? Cos pi. Let me draw a picture of my pi graph here. Pi is right in the middle. Pi is right in the middle. And so I've got minus 1 down here. So cos pi is minus 1. So then I've got minus 1/2 times minus 1, which means I've got 2 over root 2 plus 1/2. And then I can actually, well, we could stop here, or you can go a little bit further if you wanted to rationalize that denominator. You would end up with 2 root 2 over 2 plus 1 over 2, which would mean that you end up, when you combine them together, 2 over root 2 plus 1 over 2 as your final answer. Those are 2 examples of using the fundamental theorem of calculus with trig integrals. The homework for this matches up with 14E and F in the textbook.